So this is the last class before Thanksgiving break, and I absolutely must finish the central limit theorem and our discussion on that just to finish the unit. We will have a mostly complete proof modular result from Fourier transform theory. If people want to see that, I'm happy to talk about that. I'll talk about related results involving the Laplace transform. There are a huge number of transforms. There's the Laplace transform, the Mellin transform, the Fourier transform, to name 3. Frequently, you can convert from one to another by doing an appropriate change of variables. And it just depends on where's your function defined. Do you want to have your function defined from 0 to infinity? Do you have it defined from minus infinity to infinity? Well, you can go back and forth between the two of them with an exponential or logarithmic change of variables. If you're from 0 to infinity, take the logarithm, and now you run from minus infinity to infinity. So depending on how you get the data, sometimes one version is more convenient than another. Frequently, textbooks will only prove one version, and so you then just do the change of variables, convert to the version you need, and then you just quote all their results. So for me, it's often hard for me to find books that have proofs of Mellin transforms, but I can find books that have proofs of Fourier transforms, and you just go back and forth. Okay, so we were talking a lot about the central limit theorem. And we had the following danger. We had f1 of x was 1 over square root of 2 pi x squared e to the negative log of x squared over 2. And we had f2 of x equaled f1 of x times 1 plus, I believe it was the sine of 2 pi log x. And what was the difficulty with these two distributions? Good. Half integral moments agree. So what this tells us is that probability is a hard subject. It really belongs as a post-core class if you're going to do it properly, because we have to take into account you can have two probability distributions that have all equal moments but are not the same. So the question, what info is needed to assert two densities are equal? And what do you think equal means here? Somebody who's taken an advanced analysis class. Up to measure 0. Up to things that don't actually have any mass. You know, we're allowed to change our distributions on finite sets, on countable sets, on sets of measure 0. That's going to be fine. So that's one question. The next question is, what about convergence of a sequence of densities to a density? So in one case, I tell you ahead of time I have two densities, and I want to know if they're equal. Another one is I have a sequence of densities, and I want to know if that sequence of densities converges to a given density. We do not want to work directly with the densities. These are painful calculations to do. The convolutions are not nice. One of the whole points of all the different integral transforms that we're looking at is they convert convolutions to multiplication. Sometimes it's additive convolutions, sometimes it's multiplicative convolutions. It depends on whether or not you're using Fourier transform or Mellin transform. Well, that's not so surprising because they differ by exponentials or logarithms. It makes sense that you should be passing from things are nice by addition, things are nice by multiplication. So recall the moment generating function of x was the expected value of e to the tx. It's the integral from minus infinity to infinity of e to the tx fx of x dx. And this is the moment generating function. And we sketched a proof of the central limit theorem last time. And we looked at, Zn was equal to x1 plus xn minus n times the mean divided by sigma square root of n. And we showed that under nice conditions, the moment generating function converges to the moment generating function of the standard normal. Now, what does it mean for the moment generating functions to converge? Well, if you think about the Taylor series, that should probably tell you the coefficients are going to be equal. But is that enough to give you convergence? Well, one thing, of course, is we probably want the moments to actually exist. So did anybody calculate the moments of these two densities, or the half-integral moments of these two densities? So I got, I believe, moments above e to the n squared over 2 for the nth moment. Okay, so I'm just looking at my notes, and I believe that essentially that's what we get. Okay. What can you tell me about these moments? What kind of numbers are these? Real? Positive? No. I mean, what do you think I care about when I'm looking at moments like this? What property of these numbers do you think I care about? How fast they grow. I care about the rate of growth. Is this going slowly or rapidly? Very quickly. This is a YouTube video where little kids might be seeing it, so I know you're being careful as to which words you use, but you would want to use extremely strong words for how rapidly this grows. Let's look at the moment generating function of x1 of t, which is the moment generating function of x2 of t from before. So this should be the sum, n goes from 0 to infinity, of e to the n squared over 2 over n factorial t to the n. For what value of t does this converge? 0. Only converges if t equals 0. And an easy way to see this is e to the n squared over 2 is e to the n halves. Let's see, how do we want to do this? Let's be careful as to how we do this. To the n over 2. Yeah, we'll do it this way. And we want to get a sense of how large is e to the n squared over 2. What can you tell me about e to the n over 2? How big is that? So you want to get some feel for sizes of quantities. We want to compare this to n factorial. N factorial is about n to the n e to the minus n square root of 2 pi n. So this is growing about as fast as n to the n. A little bit slow, like n over e to the n, but really this is going on the order of n to the n. Is this going faster or slower than n to the n? Faster. How can you tell?
Because e to the n over 2 is going to dominate n.
It's going to dominate n. If I look at the Taylor series of e to the n over 2, if I take the square term, that'll be n over 2 squared over 2. That'll be something of size n squared. So this is going to be greater than or equal to n squared over 8. And I'll write the 8 as 2 factorial times 2 squared, just taking one term in the Taylor expansion, and then raising that to the nth power. I have an n to the n, which is going to be greater than this, and then I still have an n over 8 to the n, which is clearly going to be much better than e to the minus n. So this is enough to show that this moment generating function does not converge for any values. Even if we talked about the complex one, we might have some issues. Well, there we're going to have convergence, but maybe we're not going to have a good expansion. So I'm hoping that this gives you some sense of the difficulties. I don't want to go into a whole course on probability, but I want to give you enough to give you some flavor of what's going on and what the trouble is. All right, so I'm going to get rid of this, bad density now. But you want to keep examples like this, if you want to go into analysis, in the back of your pocket. You should have the function e to the negative 1 over x squared. This is another great example of a bad function that, if you need a problem, look at this one. Cauchy distribution. That's another good one to think of for probability. The density is nice. You have a really nice cumulative distribution function. You can do the integrals, but it doesn't have variance. So let's consider two nice random variables. We will name them, not surprisingly, x and y, with densities, say, f of x, f of y. I'm not going to go into the full detail of all the conditions we need to make this work. This is in the notes I gave you. This is meant to give you a sense of what's going on. So let's assume have equal moments for some set Rn where Rn accumulate. So as soon as you know Rn accumulates, what do you know about the sequence Rn? So what must be true about the sequence if it accumulates? Do we know anything about the sequence? It's got to be infinite. If it's finite, it can't accumulate. Could it be 1, 2, 3, 4, 5, 6, 7? No, it has to accumulate at some finite value. So there's got to be some finite value R such that no matter what small ball you draw around it, you're always going to have a moment where they agree. So this implies there exists a finite R such that for all epsilon, there exists an n such that R minus Rn is less than epsilon. So we will have infinitely many moments near R where they agree. Let's define h of x to be fx of x minus fy of x. What would you conjecture about h of x? What's a reasonable conjecture to make about h of x? So we've got two nice densities. Nice is a technical term, and depending on how much math you know, nice is weaker. The less math you know, the stronger the word nice is. We have a sequence, an infinite sequence of moments where the densities agree. We're going to let h be the difference of their densities. What do you conjecture is true about the difference of their densities?
It's 0 almost everywhere.
Yeah, it should be 0 almost everywhere. H of x should equal 0 almost everywhere. For those of you who have not taken a measure theory class, please do so. If you're not able to do that by next week, almost everywhere just means except on a set where the measure is 0, except where the integration on that set does not matter. Think of it as the rationals inside the irrationals. So we want to show that h of x is identically 0. Let's define a new function. We want to define some function related to h of x. The whole point is we want to use complex analysis. So if we want to use complex analysis, what theorem do you think we want to use? So what theorem do you think we want to use? Based on what we have on the board. The purpose of this lecture is also to review what we've been doing this semester. Yeah, we probably want to use something about accumulation points as that's the big ingredient we have. This is the difference between complex analysis and real analysis. You know, as an aside, and I'll erase this in a second, consider the function x cubed sine of 1 over x. By putting an x cubed over here, I make this function differentiable. This function is 0 infinitely often as we get closer and closer to the origin. It's well defined at the origin, but this function is highly oscillatory and is not identically 0. So even though this agrees with 0 infinitely often, what must be true then if we look at z cubed sine of 1 over z? Not holomorphic. Because if it was holomorphic, then they would agree infinitely often, and it would be identically 0. Since it's not identically 0, it must not be holomorphic. So in some sense, we don't even have to calculate or try to calculate the derivative. We know the derivative can't exist. So let's define az to be the integral from 0 to infinity of x to the z h of x dx. What does this kind of look like? What's this? What are we really studying here? I'm sorry? No, that's a z, not a 2. The zth moment. It's like the zth moment. We're basically saying the zth moment of h. Or if you want, you know, basically the zth moment of x minus the zth moment of y. And we often put primes to indicate that it's uncentered moments. So it's the difference in moments. Why would this be a good function to look at? I mean, it involves moments. So we're trying to study moments. It seems like a natural thing to do. What else is good about this function? Do we know its values anywhere? Ah, h of Rn equals 0. So the limit as n goes to infinity of a of Rn equals 0, we're assuming Rn goes to R. Because, you know, if Rn has more than just one accumulation point, it's enough to just pass to a subsequence. We don't need those extra points. We just need one place where it accumulates. So this is a really good function for us to study. We know that this function is 0 on a set that accumulates. What can we conclude? Or what would you like to conclude? Want to conclude a of z is identically 0. Why might we not be able to conclude that yet? Yes?
It depends on the initial densities we started with. In terms of if they're holomorphic, then we're just integrating something which is holomorphic.
Well, let's be careful. I mean, what's nice is we have lots of variables in play right now. Which is the variable that controls holomorphicity? And that is a word. Z is the variable that controls holomorphicity. Does it matter if H is holomorphic or not? No. We are creating a function of Z. And we're applying our tools from complex analysis to this function, A of Z, not to anything directly related to H. We're looking at a sequence of complex moments. In random matrix theory, one of the subjects I study a lot, an enormous amount of work is done by looking at complex moments, at sequences of moments, and dealing with convergences there, and then getting the results you want about the initial distribution. This is not the best proof. If I was tasked with proving the central limit theorem rigorously, I would not go through this argument at all. But this is not my assignment. My assignment is to teach you complex analysis. And I want to show you how complex analysis comes into play. I want to show you how these issues arise. I want to show you the powers of things like the accumulation theorem. And so I would much rather go through a slightly longer digression like this because it highlights some really good ideas. Why can't we immediately conclude right now that a of z is identically 0? Or can we? Is there anything that's preventing us from concluding this? What?
I mean, we're not convinced it's all over.
Okay. So we need A to be holomorphic in Z. And if you just think back to what we had a moment ago with the sine, with z cubed sine of 1 over z, that was not holomorphic. Remember, so like z cubed sine of 1 over z is not holomorphic at z equals 0. And where was our accumulation happening? At 0. So we need to determine whether or not a of z is holomorphic. It's wonderful. We go back to basically day 1 of the course, trying to determine if a function is differentiable. All right, can anybody give me any ways to try to determine if the function is differentiable? Good. I was hoping somebody would say that. I don't want to do that, but that's at least something we could try. We could try to do the Cauchy-Riemann equations. What else could we do? So, want a holomorphic. One method is Cauchy-Riemann. And what's nice about this is this gets our two favorite mathematicians on the board together again. What else could we do? Go back even further, go back all the way to Calc 1. Just compute it. Definition of the derivative, right? Those are really the two ways we have to prove something's differentiable. When we're trying to prove that these things are differentiable, we need the integrals to converge. So we're going to need some assumptions about f and g, about fx and fy, which will give us some related assumptions about h. We want to make sure that this integral converges, and we want to make sure that its derivative converges. So a prime of z would be the limit as h goes to 0 of 1 over h, and then we'll get the integral from 0 to infinity of x to the z plus h minus x to the z h of x dx. Is this correct? So this is a really good way to carefully review our analysis. Have I written anything wrong here? I'd like to think I know the definition of the derivative at this point in my life. If I had put the limit inside the integral, would that be the definition of the derivative? No. That's what we have to be careful about, switching the orders here. If I do things like this, we're okay. And so I have the limit on the outside. If we tried to do the Cauchy-Riemann approach, what would we have to justify? So if we're going to do the Cauchy-Riemann approach, we have to write a of z as u of z plus iv of z. What would we have to justify? Not the limit. Because Cauchy-Riemann, we don't have a limit, we have something else. We have the derivatives. So if we wanted to use the Cauchy-Riemann equations, we would have to justify interchanging a limit and an integral. In real analysis, you hopefully have talked about when you can interchange operations. As you have hopefully talked about that, I will not talk about that in this class, but just leave it to you to know that there is supposed to be a way to justify this. When Cameron was 2, I trained him how to wave his magic bubble wand to justify interchanges. I will try to post that video. It's extremely powerful bubble wand. You are highly encouraged to get one of these if you want to continue. Otherwise, you have to spend a lot of time justifying. When you look at this, are you afraid of this integral converging? So the question is, does this integral always exist? I can think of some values of z where this integral might not exist. If z is a negative number, then I'm going to have a 1 over x that could be very bad. But what do we know about the real part of z? If we're talking about they converge on a sequence of moments, what do you think that's going to include? What kind of moments? So this should be a sequence of real moments, right? The Rn's are real. As Rn's are real, we can probably assume maybe R is greater than or equal to 0. The question may be a little bit harder if R actually equals 0 and we have to do one-sided limits. So maybe for simplicity, maybe assume the limit as n goes to infinity of Rn equals R is greater than 0, just so we stay away from the danger that, because if they converge just at 0, if I try to take my derivative, I've got to go a little bit on the other side. Whereas if I assume they converge to some R that's positive, then I'm going to be fine. So we'll make that as a simplifying assumption. All right, so the question is, does AZ equals integral of 0 to infinity x to the z h of x dx exist? Well, we know if we take the absolute value, this is going to be less than or equal to the integral from 0 to infinity of x to the real part of z, h of x. And I'm going to write h of x as fx of x plus fy of x. This is clearly going to be an upper bound. Will this integral exist here? So this would essentially just be the real part of zth moment of x plus the real part of zth moment of y. So the question becomes, what are we assuming about our distributions? And so, let's see if I can get the camera to swivel. No, I'll have to do it manually. All right. So the question is, what are we assuming? Maybe assume only know integral moments exist. Maybe we only know that the integral moments exist of our distribution, and maybe we have some sequence. Well, one of the nice tricks we can do is let's let k be less than or equal to the real part of z, which will be less than k plus 1. There's always going to be an integer k such that this is true. And now what we have is this is bounded by the sum of the kth and k plus first moments. And the reason is x to the real part of z is going to be less than or equal to x to the k plus x to the k plus 1. So this is an extremely useful identity. Oh, I'm sorry, inequality. Why is this true? So why would this inequality be true? Do you have a thought?
Well, if x is greater than or equal to 0, then it's bound. Then x to the real part of z is bounded above by x to the k plus 1, and if it's less than 1, then it's bounded.
Good. So if x is greater than or equal to 1, x to the real part of z is less than or equal to x to the k plus 1. And if 0 less than or equal to x is less than or equal to 1, then x to the real part of z is less than or equal to x to the k. So we use two different bounds depending on the size of x. This is a very common technique in analysis, is break your argument up into lots of smaller arguments where you have good control. And so in one region we use x to the k plus 1, in another region we use x to the k. All these integrals exist. So the integrals exist without any trouble. And then we should be able to take the limit, and we should be able to pass the limit inside the integral. Okay, so let's see. I'll come over here. All right, so now, so consider a prime of z is integral from 0 to infinity. So what is the derivative of this going to be? So if I pass the limit inside, what do I get? Well, yeah, I mean, I want to take the limit. So I want, what's the limit as h goes to 0 of x to the z plus h minus x to the z over h. So essentially, it's what's the derivative of x to the z. So what's the derivative of x to the z? It's not z x to the z minus 1. How should you write x to the z? We should write x to the z as e to the log x, or e to the z log x, right? And then when we're taking the derivative with respect to z, well, it turns out this is a nice holomorphic function. And now we'll just have a log x come down. So we'll get x to the z times the log of x times h of x dx. And we want to make sure that this is well defined. It should be from the arguments we've been making, but maybe in the limit somehow things go haywire. Well, there's only two danger points for log of x. What are the two danger points? We're looking at this integral. What's the danger from the log x? Two places. When it goes to 0, and when it goes to infinity. Well, when it goes to infinity, that's no problem, because log of x is slow. So as x goes to infinity, the log of x is less than or equal to x to the epsilon, so you're OK. The integral will be bounded by just a higher moment. Integral bounded by a higher moment. So the integration is not going to be a problem at all as x goes to infinity. What about as x goes to 0? That's worse. So as x goes to 0, unfortunately, the log of x is blowing up. It's going off to negative infinity. We're going to assume h of x is reasonable. X to the z, that's going to be well behaved as x goes to 0. What's going to really matter is just the real part of z. And we're going to assume the real part of z is at least 0. Note, as x goes to 0, the integral from epsilon to 1 of log of x dx. What's the antiderivative of log of x? I'm sorry? Not x over log x. It's x log x minus x. Fastest way to prove this is the method of divine inspiration. You write down the antiderivative as x log x minus x, and then you take the derivative, and you see you get log x. It's a wonderful method. Strongly encourage you to use that on the exam. Now, if you take the derivative of x log x, use the product rule, derivative of x is 1, there's your log x. And then you get x times the derivative of log of x, which is 1 over x, which gives you a 1. So just the x log x differs from log x in derivatives by a factor of 1. So you need to subtract something whose derivative is 1, there's the log x. We now evaluate this at 1 and epsilon. Well, when I put in x equals 1, there's no problem. And when I put in epsilon, I get epsilon log epsilon. So the epsilon log epsilon piece, that goes to 0 as epsilon goes to 0. And the reason is log epsilon blows up much, much slower than epsilon goes to 0. How would you see that if you wanted to prove epsilon log epsilon goes to 0? It's probably not a bad idea to just review a bunch of things from previous classes. How would you prove epsilon log epsilon goes to 0? Any thoughts as to how you would prove this?
Write it as a ratio and
Okay, how would we write this as a ratio?
log epsilon over 1 over epsilon.
So we could write it as log epsilon over 1 over epsilon, and then let's just let u equal 1 over epsilon. Then over here, this is the same as negative 1 over epsilon. And now this is just negative log of u over u. And what do we apply? Right. So as epsilon goes to 0, we have u goes to infinity, apply L'Hopital, and that will yield the derivative of negative log u, will be minus 1 over u, and the derivative of u is going to just be 1, which goes to 0. So that's a way to prove that epsilon log epsilon goes to 0. So we're actually not worried about this integral. The integral is going to be well behaved. Okay. So this function is fine. So a of z is basically complex differentiable. I'm being a little cavalier in justifying the interchange of operations. These are results you should have seen in real analysis. I'm trying to give you the flavor. And I'm trying to let you see why complex analysis comes into play. And now we can use our accumulation results. So good. So I was trying to be careful and not erase the board over here. We have all these wonderful results that since a goes to 0, along a sequence that accumulates, a must be identically 0. Because a is complex differentiable. So our function a is identically 0. So now we can write over here, it is holomorphic. Does this finish the proof? Can we now conclude h is identically 0 or 0 up to a set of measure 0? What do you think? We know h is fx minus fy. We know a of z is identically 0. Does that mean h is identically 0? So I'll write the question over here. Does everyone agree that that is what we've reduced it to? We know a of z is identically 0. So the integral from 0 to infinity of x to the z h of x dx equals 0 for, say, real part of z greater than 0. Does this imply h is identically 0? Is h of x equals 0 almost everywhere? What do you think? Can we now conclude that h is identically 0? Or do we need to do more work? We know a transform of h gives an expression that's identically 0 for all z. So we start off with h, we apply some operation, and we get some new function, which we're calling a. And we know this new function is identically 0. Can you give me one function h such that when I take this transform I get identically 0? Yes. So we know clearly if you start with 0, you end with something that's identically 0. The danger is, could there be something other than 0 that gets mapped to 0? And that's where we need to be a little bit more clever, and that's where we need to somehow invert the transform. And basically say the only element in this space that is sent to 0 is the function that's identically 0. And this is where you then start to use some assumptions about fx and fy, so that you can then use the inverse Fourier transform. And if we choose z to be imaginary, we're getting basically a Fourier transform. We maybe have to, right now this is set up more like a Laplace transform. We have to convert to Fourier transforms or just build up the theory from Laplace transforms. Doesn't really make much of a difference. We need to somehow invert this. Another thing we could try to do is we know that any finite linear combination is 0. So we could try to build up a series approximation. So we know that the integral from 0 to infinity of a sum of a n x to the n goes from 0 to n, h of x dx is identically 0. We would love to say, imagine h is not identically 0. So imagine there's some x naught where h looks like this, and by continuity it's positive. We would love to then say, well, let's just choose appropriately so that we have a function that basically is 0 into here, spikes up, and spikes down. Unfortunately, we need to do that with finite polynomials. And then this starts to lead into the subject of polynomial approximation theory. If we knew that the function h had compact support, it would be a lot easier. And then you could make this argument work without too much trouble, because then we're just trying to have a really good, not an issue. But because things have to go all the way off to infinity, well, eventually this is going to be blowing up. I don't care what you choose for the ANs. If a sub big N is not 0, then eventually this is going to look like x to the big N. And it will not be looking like 0 far away. It'll start growing polynomially. So on compact intervals, we could probably make this work. But this all leads down to we need some understanding of how to invert transforms. Okay? And that's the result from Fourier analysis that I'm not going to do, is that if you have a sufficiently nice function, there's something called the Schwartz space, which Blake may or may not be talking about later today, then the Fourier transform is invertible, and the only thing that will work here is the function that's 0. That's the final nail we need on the coffin. But what I like here is this highlights a lot of the key ingredients you've been seeing, hopefully, I'm hoping, in your analysis classes over the years. The difficulties of interchanging limits. Going back to the definitions as to what do we mean by derivative? How do we calculate these things? What do we mean by x to the z? We go back to the exponential. How do we bound something? we split it into two different parts. If x is greater than 1, we use this bound. If x is less than 1, we use that bound. And because there's only two bounds, we can easily amalgamate them and get a bound that's manageable. If we had infinitely many bounds, problem. This also highlights the difficulty of working with infinities. If we had a compact interval where all the action happened, much, much easier. Okay, any questions on this argument? What I want to do is we're not going to have time to go into details of the Laplace transform. I'm going to just state what an integral transform is and then leave you with a Thanksgiving challenge. My great physics mentor, Professor Firk, gave this to me my freshman year in college before Thanksgiving, so I would have something to talk about over the table. Sadly, I did not go to the appropriate Thanksgiving. So I'll start with just an integral transform. And this is unrelated to the challenge. So we have some function f, and we're going to map to some transform function. And we're going to have some function k of two variables. And this will be called the kernel. And basically, f tilde of y is going to be the integral from minus infinity to infinity of f of x times the kernel of xy dx. So anything of this form is going to be called an integral transform. And you start off with f. This function k gives you a new function of y. Different choices of k will lead to different things. We've looked at, maybe k of xy is equal to e to the negative 2 pi I xy. And this will give you Fourier transforms. You could look at k of xy is e to the xt. And this will be related to like the Laplace transform and the moment generating functions. So you can view all of these in a unified way. And you can develop a theory of integral transforms where these are just special cases. Yes?
Are there restrictions on k, or can it be any function?
It can be any function, but the wilder k is, the less likely it is to be useful. And so the whole point is to find choices of k that will lead to things that are doable. All right. So the Thanksgiving fun. And so this was related by Professor Firk, my mentor, who is a physics professor at Yale. So define the operator integral on f to be the integral from 0 to x of f of t dt. Okay? So I'm just defining an operator like this. I can define any operator I want. I claim this is going to be a fun operator to study. I want to solve the integral of f equals f minus 1. Can anybody give me an example of a function that would solve this? Don't have much time. Be inspired quickly. So I want a function. So when I integrate it from 0 to x, I get back the function minus 1. So I want its value at 0 to be 1. When I integrate it, I want to get the function back. What function do you get back when you integrate? E to the x. Think f of t is e to the t. That should be the solution. All right, here's the quick proof. Well, if I want to solve this, this is the same as f minus the integral of f equals 1. Just moving things around. This is the same as 1 minus integral acting on f equals 1. Now let's apply the operator 1 minus integral inverse to both sides, and we get f equals 1 minus integral inverse applied to f. Well, we know what, I'm just applying the operator 1 minus integral inverse, right? So this is 1 plus integral plus integral integral plus integral 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 applied to f. What am I using here? Geometric series. So I now, so I can give this one. So now this is equal to, f is equal to f plus integral of f plus integral of f plus dot dot dot. Okay. So this is applying the function 1 to f. So applying. Oh, this is not f over here. I'm sorry. This is 1. I'm sorry. This is 1 over here. Sorry, it's 1. All right, so it's 1, integral of 1, integral of 1, etc. All right, 1 is just 1. What's the integral of 1 from 0 to x? Quickly! X. Now, the integral of 1 is our function x. Now we have to integrate that from 0 to x. We get x squared over 2. What's the next term going to be? We now integrate the function x squared over 2 from 0 to x. X cubed over 3 factorial. And so we get f of x is e to the x. Justify. So figure out a way to make that rigorous. All right, happy Thanksgiving. It can't